Okay, thank you very much. Thanks for that kind introduction. And it's always a pleasure to be back at ODSC. This is 2022 to present at this session on AI for Good. I suppose by way of a brief introduction, my background is in biomedical engineering, and I lead the Planetary Health Informatics Lab at the Center for Statistics in Medicine at the University of Oxford. And I just maybe want to give a disclaimer that I personally can take very little credit for the work that we're going to go through now. This is a work of a huge team here at Oxford and collaborators abroad. And so I'm just the lucky person invited by ODSC to present this overview of what is the work of many colleagues in the field. So over the next 40 minutes or so, we'll go through an overview of health inequity and the role of artificial intelligence, and explore ethnicity data that is collected in routine healthcare settings, with a view to moving towards health equity via AI. And so the talk is split into two parts covering these three areas. I should also maybe mention at this point that something that we won't cover in this talk is machine learning theory. So there are plenty of talks at the ODSC that are in-depth machine learning theory. In fact, if I've done this right, you may be pleased or disappointed depending on your background. There will be no maths at all in this talk today. So with that, let's look at this issue of health inequity and the role of artificial intelligence. So by way of background, inequity in health is something that was highlighted hugely by the COVID-19 pandemic, where people from ethnically diverse backgrounds were disproportionately affected with higher mortality rates, higher ICU admissions, and hospitalizations. But we know that inequity is something that's not limited to COVID. It's something that's unfortunately a long-standing international, multifaceted, in fact, issue. And there are many contributing factors. It could be poverty, environmental and climatic vulnerability, gender imbalances, racial imbalances, societal norms, and the list sort of goes on. These words that were spoken in the fight against the COVID pandemic, in a way, actually capture the idea of inequity, i.e., a situation where not everyone is equally safe and has equal access to healthcare. And this problem of inequity comes with sobering costs in terms of human lives. In fact, this work published in the BMJ nicely illustrates this idea of a sort of a positive feedback loop, where lack of access to healthcare in the first place can lead to a lack of representation in healthcare data. And then unrepresentative or biased data can in turn lead to biased artificial intelligence models that, when then used with patients in the real world, can lead to inappropriate care. That in turn can exacerbate underlying systematic inequities. So a vicious cycle of sorts. And one factor in inequity is through that of health technology. So to explore this further, an example is that of AI technology for clinical risk prediction. And in very simple terms, this is something that would typically involve routinely collected anonymized patient data, which is then fed into an AI model, which then produces a health risk score or some sort of a calculator. And that is used by doctors to decide patient care, to make decisions. If there's bias in the data or bias in the model, doctors can potentially make wrong decisions, and patients can potentially get the wrong sort of care, or indeed no care at all. So this bias can creep into the system in many ways. First, in the data, the issue of health data poverty, where there may not be enough patients from different ethnic groups, or ethnicity may not be correctly recorded. Then there's the issue of algorithmic bias. So models may not either include ethnic patients at all. There are many examples around. One is that of a tool to predict our cardiovascular risk, such as Framingham. It's a commonly used tool to assess everyone's heart health, but was made for an affluent group of Caucasian individuals based in the US, North America. Pulse oximetry is something that became a classic case in point when oximeters were trained on data from white ethnicity and were not calibrated to other ethnic groups, misestimating oxygen levels, which was a key indicator in case of COVID severity. In case of COVID risk prediction models used for shielding and vaccine prioritization here in the UK, anyone with missing ethnicity was initially assumed by the models to be of black ethnicity. Anyone with missing body mass index was assumed to be obese. And this was found to overestimate COVID risk for over 400,000 people who were from black backgrounds, young men, women who were pregnant, and all of these had to be the risks had to be corrected later at the height of the pandemic, where healthcare resources were already stretched and vaccines, as an example, were scarce. In fact, looking into this issue of modeling bias, a study led by our department found that the most all of the prediction models built for COVID-19 risk prediction were at high risk of bias and therefore not suitable for triaging patients in actual clinical practice. So, considering these mechanisms of algorithmic bias, one of them is the issue of race correction. And maternal mortality, which is something that is a global indicator of health inequity, you might be surprised to know that in the US, the US has one of the highest maternal mortality rates among some of the richest countries of the world. Race correction has been used in algorithms to decide who should and shouldn't have a C-section for childbirth. And so, in the words of the author of the study, this is thought to disproportionately point people of color towards a potentially riskier procedure, that of C-sections, reinforcing extreme inequities in maternal medicine. And so it was found in the study that Black women were 3 to 4 more times more likely to die as a result of um, C-sections during childbirth. Another example of algorithmic bias is that of the use of something called proxy predictors. Now, this is another famous case in point where healthcare costs were used as a proxy for ill health to predict the need of healthcare insurance patients. And by overestimating patients who paid more insurance, it was found to marginalize patients, often people of color, who were just as sick, maybe, as white people, but did not pay as much insurance. So, in a way, people of color had to be more sick than white people to receive care. And the authors were of the opinion that without the inherent bias in the algorithm, around twice as many people of color could have benefited from better care at the point of need. In fact, there's a long list of models with with issues to do with bias published in the New England Journal of Medicine, and just in the realm of clinical risk prediction models from all sorts of clinical fields, such as cardiovascular to oncology, neurology, all the way to obstetrics. And there's a range of ways in which models can be biased, including the issues covered, but also ignoring interactions with ethnicity and other social determinants, and the issue of missing data and how it's handled. So, such assumptions on the whole can lead to oversensitive models, but more importantly, can misestimate a real person's health risk, which means that at an individual level, patients can get wrong care, and at societal levels, some groups of patients might inappropriately be over or under prioritized, which in turn can affect patient and public trust. So, such is the power of inequity via AI, be it through models or through data or a combination of the two. And now, where is all of this data in healthcare coming from? So, everywhere, electronic health records, registries, biobanks, claims databases, and even digital devices, self-reported data often comes from digital devices. Now, many of these sources are digitized, which means that they may represent a skewed section of the population in terms of both sociodemographics and clinical history. And for data to be bias free, it is important that the data are representative of the general population, or everyone in the population of interest. And this sort of skew was illustrated nicely by a global review recently of around 200 health data sets from all over the world. And it was found that it was US and Chinese data sets as well as authors that were disproportionately overrepresented in the clinical AI. Almost all of the 10 top databases and their author nationalities were from higher income countries. AI techniques were most commonly employed for image-rich specialties such as radiology, and authors were more or less predominantly male. So this goes to show some of the disparities in the data that exist within and between populations, as well as across different demographics, disciplines, and diseases. So now, coming back to this rather simplistic depiction, to go from being a source of inequity to a solution for health equity, it's almost a case, one could argue, where a case of reverse engineering in a way, where to fix inequity via AI, we must first have good data, data that is ethical, well governed, fair, and one that is importantly representative of everyone. And ethnicity is one way to capture this sort of data representativeness. So let's go and look at some of that next. So with this, let's move into the second half of the talk, which is about exploring routinely collected ethnicity data in healthcare. The data sources that we're looking at include two trusted research environments. A trusted research environment is a federated model to facilitate safe use of pseudo-anonymized health data from patients. NHS Digital covers healthcare records from GP practices and hospital records from England in the UK, and contains records for about over 55 million, and now going into over 60 million patients from the UK. There's also a similar database from Wales, which is called SAIL, and that contains records for everyone registered with GP practices in the region of Wales in UK. And the types of data include primary care data sets such as GDPR, and this is linked with secondary care, hospital admission statistics for England, and this is linked with the Office of National Statistics for mortality and deprivation data. Access to these data are coordinated by the Health Data Research UK and orchestrated by the British Heart Foundation. So this study or this talk focuses on data from the NHS Digital dataset. And this snapshot here is just to give you a flavor of how ethnicity data within the NHS Digital TRE is organized. And this here is capturing over 490 ethnicity groups that are covered by the over 55 million patient records. In terms of the types of ethnicity data available, mainly two types of codes are captured across a number of primary and secondary care settings. These are called primary codes, and the other is SNOMED CT codes. So the primary codes follow what is known as an A to Z notation that follows the Office of National Statistics census categories here in the UK. Although there's no official mapping between the two, but broadly primary codes follow census categories. And these are available from these are available in the GP data from primary care as well as hospital records. The other main form in which ethnicity information is captured in routine care is via SNOMED CT codes, which are only present in primary care data, not used in hospitals. So although nearly around 500 or so codes exist, only about half of them are actually used in real practice. And if you consider the definitions of SNOMED codes for ethnicity, there is quite some variety, where some SNOMED CT codes capture information about race and ethnicity, others capture information about religion, country of origin, languages spoken, and so on. And so as an example, as you can see here on in the slide, the top map shows that about 80% of the SNOMED CD codes contain the name of a continent or a country, whereas if someone were interested in country level information, only about 50% contain the name of a country. And that's just the geographical information contained in some of the SNOMED CD codes. Now, in terms of how different types of codes are mapped to one another, one could almost think of this in terms of a pyramid where SNOMED CD codes are right at the bottom. These can then be collapsed into primary codes, and then primary codes are further grouped into what are known as higher level ethnicity groups, or most often by researchers for study purposes. And this is one way to visualize this mapping. An interactive visualizer is available on the study website, or soon to be available on the study website if someone was interested to have a look at that. Now, to move towards sort of looking into these data in terms of completeness and correctness and granularity, which is important or essential in order to assess whether ethnicity data are biased or not, and therefore uh, suitable for artificial intelligence models. Let's have a look at some of the numbers. So here we have ethnicity data in primary care records. So out of a total of around 61 million individuals in the general practice, about 86%, those in the red box on the right, have at least one record of ethnicity as part of their electronic health records when they present to their doctor in the general practice. And the distribution of ethnicity for this group is something like this, where about 77% of ethnicities recorded in general practice are of white ethnicity, whereas um, there are there are higher proportions in this healthcare data of those of mixed black and missing ethnicity as compared to census data. Bearing in mind that these numbers also contain about 3% missingness in ethnicity records, and these are just numbers for England. Now, for those who did not have an ethnicity record at all in GP data, that was about 14% of those. The question was, um, how can their ethnicity data be um, extracted or completed? And so, after a lot of discussions with patients and public representatives, it was understood or considered that inference or imputation should only be used as a last resort, because therein you're making, again, inferences and guesses about people's backgrounds, and where we are talking about biases, that is in fact um, can be a contributor of exacerbating bias rather than um, the other way around. And so to address this, the approach taken for missing data was to try and link ethnicity records from hospital records and other tables known to have good quality ethnicity information. And so, in short, what was found was that by doing this sort of linkage, the missingness and in ethnicity records in primary care dropped by 10%. So that was good news. It was also found that beyond hospital admission records, uh, there was not much more ethnicity information, additional ethnicity information that could be gleaned from other tables, other healthcare tables. In terms of looking at the characteristics of those who had an ethnicity record versus those who had no information on ethnicity recorded in their healthcare records, and this is something that confirms what we already know from literature as well. It was found that those for whom ethnicity was either not recorded or it was not stated, that was this group included mostly younger people. There were more men in the group. They were healthy people, and where ethnicity was missing, there was generally more missingness on the whole. In terms of, for example, information of deprivation, in terms of information on body mass index, these are just some of the checks that were done in terms of looking at overall missingness as a characteristic of this group of individuals. And so this can be seen here better in this graph here, which shows that actually missingness actually peaks around the ages of the younger ages between 18 and 40 years old, as for those who did not have any ethnicity record as compared to those who did. And some distribution or a trend could be seen in terms of geographical distribution as well, where um, there was a higher proportion of those individuals without any ethnicity record compared to those with ethnicity records in the south and southeast regions of England, which is where is considered to be more multicultural. The social demographics are considered to be more multicultural. And this again confirms what's known from literature. Then with regards to looking at correctness, in these data that were examined, we, we can see that um, for an individual who presented to to the healthcare system, you'd expect that they would have an ethnicity and that would be consistent over time. However, what was found was that ethnicity information can actually vary for the same individual. So in primary care records, so people presenting to the GP, about 17% people had multiple ethnicity records at different points in time. Whereas this number was even higher, more than twice, for those going to seek healthcare in hospital admissions. So what are the characteristics of multiple ethnicity records? And so here on the left, we can see that the distribution of an overall count of ethnicities included in multiple ethnicity records. Predominant ethnicities include white, Asian, and mixed ethnicities. But if we look at, for an individual, what are the common kind of multiple ethnicity pairs that were found in the data, we see that um, for instance, excluding or discounting white, the most common kind of multiple ethnicity pairs were Asian background with other ethnic background, African background with other black background, and so on. And this kind of goes to kind of show the complexity in the way ethnicity data is recorded in the first place, where there is a slight lack of consistency and therefore an area of improvement in terms of improving data quality. So next, looking at potential mapping discrepancies. Once the data is recorded, it is important to understand how it is mapped and how it is organized, and if there are any potential discrepancies within that. So this is just a zoomed in version of the previous plot. And if we consider the group of ethnicities called other ethnic groups, we see that um, there are two groups such as Gypsy or Irish traveler and Chinese, and they are mapped currently into other ethnic groups. This is a depiction of what might be other possibilities. So in the middle, you see SNOMED CT codes, and on the left is their current mapping, and towards the right is alternative mappings based on what could be potentially a better place for the particular SNOMEDs in question, codes in question. So for example, if you look at the case of Asian and Chinese in the red box, at the moment it is grouped into the ethnicity group um, other ethnic groups, whereas it could possibly be placed into the group Asian, and Chinese could possibly be a potentially be a ethnicity group in its own right. But this is just in a depiction of the potential variation in mapping, and is there for the experts to kind of analyze. Moving on to the third thing that was looked at in terms of looking at quality of ethnicity data, uh, and that of the issue of granularity. So here, this question led to more questions rather than solutions. So for example, we know now on investigating the data in UK that there are at least 250 and something like over 490 ethnicity codes in total in routinely collected data. But how deep is appropriate when it comes to using these ethnicity codes for research purposes to improve healthcare practices? Um, a way to maybe kind of look at this is to look at the subgroups within the group other ethnic. And so here in the boxes, the idea is to depict some possibly distinct and possibly large enough subgroups that could be distinct subgroups in their own right. So for example, Arab, which has over 100,000 individuals subscribing to that group, as well as Gypsy and Traveler, which we now know are separate groups in even in the UK census. Um, so out of all of the 55 subgroups, are there potentially some that can be studied for research purposes on in their own right? The answer to that question lies in the nature of the clinical question, but as well as the sample size considerations within that AI model. This is the same thing for the subgroups within the Black group, and here we see, for example, the Somali group is potentially a sizable group that could be studied as a group in its own right. Um, and the mixed group, which leads to more questions than it provides answers for, but also the idea that is it possible to go much deep in a group that is mixed, and where we only have the level of detail down to two ethnicities that contribute to mix, such as, for example, white and black, white and Asian, and so on. And then finally, just looking at the subgroups within the Asian group, found in the UK healthcare data, and the predominant or the top three groups here, although there are 56 subgroups in total, that of British Asian or Indian, British Asian or Pakistani, and British Asian or Bangladeshi. And here we can see that um, the sample sizes uh, are large enough, possibly, for these groups to be considered subgroups in their own right. So that research can now focus on these individual subgroups as opposed to them being lumped into the wider group of Asian. And in fact, what we started to see in more recent literature is the stratification of ethnicity groups down into these individual levels. And as an example, maybe, of how sometimes the devil is in the detail, and how these nuances can possibly make the difference um, between generating good evidence and not, is this case in point, which is where um, COVID mortality rates were only the differential between the COVID mortality rates between Bangladesh, Pakistani, and Indian groups only came to light because these groups were studied or stratified. Mortality rates were stratified by individual ethnicity groups, and it was found that, for instance, in the second wave of the COVID pandemic here in the UK, the Bangladeshi ethnicity and men of Bangladeshi ethnicity were at a higher risk, much higher risk than even other Asian groups, and at a far higher risk than um, at that of white ethnicity groups. So just goes to show the value of going deeper in some cases, but all in all, something that to be dictated by the clinical question and sample sizes. A quick word on the fact that patient and public involvement when it comes to moving towards equity in AI and understanding the ideas and issues around ethnicity and how ethnicity data, for instance, should be used. So patient public involvement is integral. As an example, in this study, the data that we're looking at, behind the data that we're looking at, there were uh, patient and public representatives on the study team, focus groups were organized, stakeholder case studies were done, and so it was an altogether a PPI co-production cycle where patient and public perspective was involved in at every step, and had an impact on the way the analysis was done. So, for instance, one of the main thing that came out was that imputation of ethnicity data is something that is uh, has some ethical connotations, and therefore should be only considered as a last resort, and therefore the direction moved into that of linkages. So in summary, in this talk, we looked at ethnicity data with regards to completeness, correctness, and granularity. And the idea being that starting with over 250, or in this case 290 medical codes, to be able to use ethnicity data for better research, it's important to have better data in the first place. And so we looked at aspects of inconsistency, uh, non-accuracy, and missingness, and looked at ways of making it more complete, more granular, and more correct. All said and done, ethnicity is one way of looking at inequity. And indeed, this talk has focused on ethnicity, but ethnicity or race is just one of many markers of social determinants of health inequity. In fact, if we look at this map of the London Underground created by colleagues at the UCL, University College London here in England, um, life expectancy generally seems to be decreasing by 1 year by every tube stop going away from the Buckingham Palace, somewhere at the bottom right of the map here. So the idea being that inequity is not just about ethnicity, it's about an interplay of many different socioeconomic determinants, and is something that is everywhere and affects everyone, even economically rich regions of the world. So with that, just to summarize, the idea of moving towards equity with AI, and that in order to do that, we need data that are more representative of different more representative of different ethnicities, but also on the whole of patient populations under consideration. They need to be more complete and more correct in keeping with the principles of rubbish in, rubbish out. Um, the need for better models, implicit biases, and algorithmic biases were covered. We know that artificial intelligence can be a force for good. There are examples from imaging that we know that an artificial intelligence model on the whole can perform with 10% more accuracy than a human radiologist. But what an artificial intelligence model cannot do is to know that the data that it was fed was biased or not. So the need to look at implicit biases, societal biases, and algorithmic biases, and the idea of involving patient and public, as well as regulators and governance stakeholders into the discussion. So just a final word of caution. This is one of my favorite slides. Is that any computer model or artificial intelligence model is meant to augment human knowledge and capability, and not to replace it. This is a statement that was emphasized by a 100-strong group of leading artificial intelligence experts, including Stephen Hawking. And in general, there's a recent move towards more responsible, more fair, and explainable AI, all essential ingredients of a more equitable artificial intelligence. And so I'd like to just end on this note in keeping with today's theme of artificial intelligence for good, with this quote from late Stephen Hawking. A word of thanks to the core study team, collaborators in the HDR UK, as well as our funders. Um, some references in case you're interested. And with that, I'd like to thank you for your time, and happy to take some questions if there are any, or move into the Q&A session.
Hi, Sarah. Thank you for the presentation. Huge amount of work to improve the data we have and don't have. One question, what are the main reasons for ethnicity changes for the same person?
Yeah, thank you, Adrian, for the question. There are several explanations, or there can be several explanations for ethnicity changes. Um, some that we have an idea about, and some that are not as well understood. So, for instance, um, when someone goes to see a doctor in GP practice, they're asked to for their ethnicity at the point of registration, and it could be that person enters their ethnicity at the point of registration, but they're asked for their ethnicity at individual healthcare encounters as well, separately. And that's a place where this kind of uh, inconsistency in terms of multiple records can come in, because of inconsistency in the healthcare questionnaires that are given to patients. So we know from discussions with patients that um, often they are asked for ethnicity information on paper forms that have different questions. So, for instance, if a questionnaire has a tick box to say other Asian, and another healthcare form has a tick box to say other ethnic, so the patient has to make a choice. That is one potential area of multiple ethnicity, how that could come in. Um, People can choose to self-identify differently over time as well. That's another possible potential source of multiple ethnicity records. Um, People can move practices and settings, healthcare settings over time. And again, it's a question of when they do move and they are asked for multiple for their ethnicity information, is are the forms consistent with the forms that they filled previously? So these are some of the possible sources. However, in an ideal scenario, there wouldn't be any inconsistency um, over time for at least one individual. And so there is a move towards trying to improve recording at source, so that patient's information is accurate and correct at the point of recording, and importantly, reflection of how they self-identify, as opposed to um, something assumed or guessed at by someone else who's looking at them and taking out their information. So I hope that helps as an answer.